All right, so today we're going to tear apart a simple electrical circuit. We're going to start with a big picture, macroscopic view, something you've probably seen before. And then we're going to zoom all the way down to the microscopic physics that actually makes it all work. Let's get into it. So here's our game plan. First, we'll look at a simple car headlight circuit. Then, we'll figure out how to actually measure the flow of charge by defining what current is. After that, we'll tackle this weird but super important historical quirk about which way the current flows. Then we'll ask, what's controlling the flow? That's resistance. And finally, we'll dive deep into the physics of what actually creates that resistance in a material.
Okay, let's start at the top with a basic complete circuit. Here we have something we're all familiar with: a battery, a switch, a headlight. You flip the switch, the light comes on. We see it every day. But what is actually happening inside those wires? What is this flow that's making that filament get white hot? To even begin to answer that, we first need a way to measure what's going on.
So, to really get a handle on that circuit, we have to quantify this movement of charge. And that means we need to define electrical current.
So formally, electrical current, which we symbolize with a capital I, is just the rate at which charge flows. Think about it like this. It's the total amount of charge, which we call delta Q, that passes through some imaginary slice of the wire in a certain amount of time, delta T.
And this picture here makes that idea really clear. You just imagine taking a cross-section of a wire, that area A, and you just count the charges passing through it over a certain amount of time. The unit we use for this is the ampere, or amp for short, named after André-Marie Ampère. 1 amp is exactly 1 coulomb of charge flowing past a point every single second.
So the formula for the average current is super straightforward. Just the total charge divided by the total time. For example, a big truck battery might push 720 coulombs of charge in just 4 seconds to crank the engine. You just do the division and boom, you get a massive average current of 180 amps. That's a huge amount of charge moving very, very quickly.
Now, that example assumed the flow was nice and steady. But what happens when things are more dynamic? What if the rate of flow is changing from one moment to the next? How do we talk about the current then? Well, this is where we need to pull out a more powerful tool.
Take a look at this graph. It shows the total charge, Q, that's passed through a wire as a function of time, t. And notice, it's not a straight line, right? The charge flow starts off really fast, and then it kind of slows down, approaching some maximum amount, Qm. The slope of this curve at any given point, that's the rate of flow at that exact instant.
And of course, what's the slope of a function? It's the derivative. So the instantaneous current, the current at a specific moment in time, is just the time derivative of the charge, dq/dt. This lets us find the precise rate of flow at any moment we want.
So let's actually apply this. Here's a very common function for charge in a system, like a capacitor that's charging up. Q as a function of t is Qm times the quantity 1 minus e to the negative t over tau. That letter tau is just the time constant, which tells you how fast the system charges. So to find the current, we take the derivative of this whole thing with respect to time. The derivative of the first part, Qm, is just 0 since it's a constant. For the second part, we just use the chain rule. The derivative of that exponent gives us a negative 1 over tau, the negatives cancel, and we're left with Qm over tau times e to the negative t over tau.
And this graph shows our result perfectly. At time t equals 0, that exponential term is just 1, so we start with a maximum current of Qm over tau. Then, as time goes on, the current just decays exponentially, getting closer and closer to 0. This makes perfect sense, right? It perfectly matches the slope of that first charge graph, which started off really steep and then flattened out.
So, we've figured out how to quantify the rate of the flow. But flow also has a direction. So, which way is the current actually going? Well, the answer is a really fascinating quirk from the history of physics.
So here's the deal. We have two competing ideas: conventional current and electron flow. Electron flow is what's physically happening in a metal wire. Negatively charged electrons are moving from the negative terminal of the battery to the positive one. But the standard that we use in literally all circuit diagrams is called conventional current, and it's defined as the direction that a positive charge would flow. So from the positive terminal to the negative.
So why do we have this totally backwards convention? Well, you can thank Benjamin Franklin, way back in the 1700s. See, long before anyone knew what an electron was, he was thinking about an electrical fluid. He had to guess which way it flowed, and he figured it would go from a place with more fluid, which he called positive, to a place with less, which he called negative. It was a 50-50 shot, and he just happened to guess wrong about the charge carrier. But the convention stuck.
Now, this slide shows exactly why Franklin's accidental convention is actually so useful. The electric field, E, always points from positive to negative. So in picture A, if you have positive charges, they move with the E field, and the conventional current I points in that same direction. Simple. Now look at B. In a real wire, you have negative electrons moving against the E field. But here's the clever part. A stream of negative charges moving to the left is electrically equivalent to a stream of positive charges moving to the right. So we still define the conventional current I as pointing to the right, in the same direction as the E field. This gives us one consistent direction for current, and it makes all the math and diagrams so much cleaner.
Okay, so we have this electric field inside the wire, pushing these charges along, which should make you ask a pretty important question. What's stopping them? Seriously, think about it. If you have a constant force from the electric field, F equals ma, right? Why don't the charges just go faster and faster and faster forever? There has to be some kind of opposing force, some kind of drag. And there is. As these charges, these electrons, try to move through the conductor, they're constantly colliding with the ions in the metal's crystal structure. It's like a chaotic game of pinball. These collisions act like a drag force. So between collisions, the electric field speeds them up, but then bam, they hit something and slow down. The end result is that they settle into a constant average velocity, which we call the drift velocity. It's a perfect analogy for an object hitting terminal velocity as it falls through the air.
And this property of a material, this difficulty it presents to the flow of current, that's what we call resistance, with a capital R. We measure it in a unit called the ohm, which we write with the Greek letter omega.
The fundamental relationship here is Ohm's law. It defines resistance as the ratio of the voltage, V, across a component to the current, I, that flows through it. So R equals V over I. This shows us that for a given voltage, a given electrical push, resistance and current are inversely proportional. You crank up the resistance, the current has to go down. It just makes intuitive sense. Okay, for our final section, let's zoom in one last time. We've defined resistance, but where does it actually come from? What physical things about a material determine how much it's going to resist the flow of current?
It turns out resistance isn't just some abstract property. It's determined directly by a material's shape and what it's made of. The formula is R equals rho times L over A. Let's break that down. Rho is the resistivity. That's an intrinsic property of the material itself. It's what makes copper different from rubber. L is the length. A longer wire means the charges have to travel farther and have more chances to collide, which means higher resistance. And A is the cross-sectional area. A thicker wire is like a wider highway, more lanes for the charges to flow through, which means less resistance.
And this isn't just a textbook formula. This is fundamental to all of modern engineering. We use this exact relationship to manufacture resistors with incredibly precise values, which we then use to build circuits. So, the next time you look at a circuit board, remember that every one of those tiny components is a physical manifestation of these exact principles. It makes you wonder, doesn't it? How many billions of these carefully engineered obstacles are working right now inside the device you're watching this on just to make it all possible?